Hello everyone, welcome to the talk Improved Bounds for Metric Capacitated Covering Problems. My name is Sayan Bandyapadhyay and I am a postdoc at the University of Bergen. Let me start with the definition of the classic set cover problem. So in this problem, we are given a ground set of elements and we are also given a family of subsets of this ground set. And the goal is to find a minimum size subfamily such that the union of the sets in this subfamily contains all the elements of the ground set. Or in other words, this subfamily covers the elements of the ground set. In the capacitated version of set cover, we are also given an additional parameter u. It's called the capacity parameter corresponding to the sets. And here also the goal is the same, but we also would like to find an assignment of the elements to the sets in the subfamily such that each set contains or each set is assigned with at most u elements. That means each set can cover at most u elements in this version of the problem. And then the goal is again the same. We would like to find a minimum size subfamily which satisfies the capacity constraints. And in a special case, if we set u to be the total number of elements in the ground set, then the cardinality constraints are true trivially, and we obtain the set cover problem. So set cover is a special case of capacitated set cover, and hence it is also hard to, capacitated set cover is also hard to approximate within a factor asymptotically better than log n. However, there is a tight log n approximation known even for this version of set cover. Now the question is there a special set system for which we can break the barrier of log n inapproximability? And with that goal in mind, we study the metric capacitated covering problem. So in the metric capacitated covering problem, or MCC, it's a special case of the capacitated set cover problem where the elements are points in a metric space and the sets are balls in the same metric space. And the goal is again the same, to find a minimum sized subfamily that covers all the points by satisfying the capacity constraints. Let me take a few examples. So in this example, say capacity is equal to 2, and here it is sufficient to select 4 balls in the solution. In particular, we select the balls which are not dashed, and we assign exactly 2 points per set or per ball. And here the points which are assigned to a ball are shown by the same color. However, if we increase the capacity to 3, then only 3 balls are sufficient to cover all the points. Okay, now the question is how hard is it to approximate MCC? And the answer is it is as hard as set cover, and one can find a very straightforward reduction from set cover to this problem. Basically, for each set we take a ball, for each element we take a point, and if an element is contained in a set, then we set the distance between the center of the corresponding ball and the corresponding point to be exactly 1. So all the balls are here unit balls, and in this example, the elements A, B, C, D, E are in S1. So the points A, B, C, D, E are inside the unit ball B1. And then we consider the distances, the metric induced by these distances, and we set the capacity of each ball to be n, the total number of elements in the ground set. And it is not hard to see that there is a one-to-one correspondence between a solution of set cover and a solution of this problem. Okay, so the question is, for the general version of MCC, it is not possible to get a constant approximation, but is it possible to somehow relax the problem so that I can still obtain a constant approximation? And our work is motivated from the following result for metric uncapacitated covering in RD for dimension at least 3. And this is basically the geometric version of set cover without capacities. And even for this problem, the base known approximation factor is log n. And Horpeleth and Lee showed that one can obtain a 1 plus epsilon approximation if we are allowed to expand the balls by 1 plus epsilon factor. And if we are allowed to expand the balls, then we get an added advantage over the optimal solution, which is not allowed to expand. So motivated by this work, we also we showed that it is possible to obtain a constant approximation for metric capacitated covering with a constant factor expansion where the factor is 6.47. So now one can ask if this expansion factor is tight, and a lower bound on this expansion factor follows from the reduction from set cover. Basically, in this reduction, one can show that if a point is not inside a ball, then the distance between the center of the ball and the point is at least 3. And thus, if we do not expand the ball by at least a factor of 3, then we do not cover any more points than the ball was covering before. And hence, to break the barrier of set cover, we need at least 3 factor expansion. And this immediately gives 3 lower bound on the expansion factor to obtain a constant approximation. And again, one asks the question that for what possible value between 3 and 6.47, one can obtain a constant approximation. And in the current work, we showed that one can obtain a constant approximation with only 4.24 factor expansion. And we also consider a generalization of metric capacitated covering, where the capacities are not uniform. Each ball has its own capacity Ui, and for any 2 balls Vi and Bj, if the radius of Vi is larger, is at least as large as the radius of Rj, then the capacity Ui is at least Uj. And in our previous work, we showed that for this special kind of capacities, one can obtain a constant approximation with 9 factor expansion of the balls. And in the current work, we are able to decrease the expansion factor to 5. And in the rest of the talk, I will discuss this result. And this result is based on LP rounding. So let me consider the ILP of the metric monotonic capacitated covering problem. So recall that we are given a set of balls B1, B2 up to Bm, and a set of points P1, P2 up to Pn. And in this ILP, we take a variable yi corresponding to each ball bi, which denotes whether the ball is selected in the solution or not. And for each point pj and each ball bi, we take a variable xij, which denotes if the point pj is assigned to the ball bi. And we also call xij to be the flow of pj from bi. And then the objective function is the sum over all yi's, the number of balls in the solution. And we would like to minimize this objective. And the ILP constraints are as follows. The first constraint is that for each point pj, pj should receive exactly one flow from all the balls, or its one demand must be satisfied by all the balls. And the second constraint says that if a point is assigned to a ball, then it must be selected in the solution. The third constraint is the capacity constraint, which says that the total number of points assigned to a ball must be bounded by its capacity. And the fourth constraint says that if a point is not contained in a ball, then it cannot be assigned to that ball. We consider the LP relaxation of this ILP, and then we design a rounding algorithm to round the fractional solution to an integral solution by losing at most a constant factor in the cost. So let me now talk about the ideas that we need for this LP rounding algorithm. And the first idea is called flow rerouting. And let me demonstrate this idea with respect to the uncapacitated version of the problem. So in the uncapacitated version, I can assign any number of points to a ball. And suppose we are given a fractional solution and we would like to round it to an integral solution without losing much in the cost. So the algorithm is very simple. What we do is in every iteration, we take a point. In this figure, it's the point A. And we also look into all the balls which give flow to this point or which serve this point A. So in this example, the blue balls, B1, B2, and B3. And then I select the largest ball among these, V1, and I select this ball in my solution and I throw away all the other balls. But note that we need to still cover the points which are not inside this ball B1, but in B2 and B3. So we expand the ball by a factor of 3. And as B1 is the largest ball, all these red points are within 3 hops away, at most 3 hops away from the center of the ball B1. And what I can do is I can reassign these points to the ball B1, or I can reroute the flow of these balls to the ball B1, which is selected in my solution. And note that to start the point A, the sum of yi values of B1, B2, B3 must be at least 1. And hence, the fractional optimal was paying a cost of at least 1 to serve these points. And as I have opened exactly one ball, I pay a cost of exactly 1. So I do as good as the optimal solution. And then I repeat this process. I select another point which is not yet covered, and I take the largest ball around it and reroute the flow. And in this iteration also, I do as good as the optimal solution. So once this algorithm terminates, I obtain an optimal solution by expanding the balls by at most a factor of 3. However, note that if we have capacities, then the simple algorithm doesn't work because I cannot read out unlimited amount of flow from the blue balls to the newly selected green ball. I can only assign at most its capacity amount of flow to this ball, and so I have to read out the flow in a controlled manner. And that's why we need some more ideas in the capacitated case. Before talking about those ideas, let me make the following simplification. So a ball is called heavy if its Y value is exactly 1. And a ball is called light if its Y value is in between 0 and half. And without loss of generality, I can assume that in my fractional solution, I have only heavy or light balls. So if we have a ball which has Y value in between 1 and half, then I can round its value to exactly 1 by losing at most a factor of 2 in the cost. And as I am shooting for a constant approximation, this is fine. So from now onwards, I will assume that we have only heavy or light balls, and the heavy balls are already rounded. We just need to round the light balls. So I will select a subset of the light balls in my solution. But I have to make sure that I do not end up opening or selecting too many light balls in my solution. So the algorithm that we use is the following. So in each iteration, we judiciously select a light ball. So here the blue ball BT in this figure. And we say that we are going to select or take this ball in our solution. But now I am increasing its Y value from below half to 1. So its capacities get increased. And so to utilize the capacity of this ball, I need to reroute flow from other balls to this ball, BT. And especially from the other heavy balls to this light ball. And now we can have two cases based on how many points we have inside this ball BT and what is the capacity of this ball BT. So the capacity of this ball is UT and the number of points inside this ball is NT. Then there can be two cases, UT is at least NT and UT is strictly less than NT. So in case UT is at least NT, we have enough capacity to serve all the NT points. So we can just assign all the NT points fully to this ball BT. And hence the flow is rerouted from other balls to this light ball BT. And this ensures that enough capacities become available for the other balls and in particular for the heavy balls. In the other case, UT is strictly less than NT, but I can still assign UT points fully to the ball BT without violating its capacity. Okay, so to analyze this algorithm, we need to ask two following questions. So the first one is that how can we systematically compute the amount of flow rerouted from the other balls or the heavy balls to the light ball? And what to do with the available capacities of the heavy balls? So we cannot just waste these available capacities. Otherwise, I am going to uh, lose those capacities, and there is no point of, and I might end up opening too many balls in the solution. So to address these two questions, we need the second idea, which is called credit system. So in the system, each heavy ball gets a credit when flow is rerouted from the heavy ball, this heavy ball, to the newly selected light ball. And the amount of credit is exactly the amount of flow rerouted from this heavy ball to the light ball. However, to give an upper bound of constant factor in the approximation, we need to make sure that in each iteration we increase a fixed amount of credit. And to make sure that, what we do is we pre-process the LP solution to ensure that for each point, at least a constant C amount of flow is given to the point by the heavy balls. That means a light ball can give at most 1 minus C amount of flow to each point. And this ensures that when we reroute the flow from heavy balls to the light ball, then for each point, at least a constant flow becomes rerouted. That means if for each point the available capacities get increased by at least the amount C. And this has a major contribution in showing the constant approximation factor. And the constant approximation factor depends on this constant. Now, how do we address the second question? So one way to do that is to make use of the available capacities to reroute flow from other light balls, or to absorb the flow of other light balls. And this ensures that I do not end up selecting a lot of light balls. And let me discuss how is that. So what we do is that in every iteration, we consider each heavy ball, and if that heavy ball has enough available capacity to absorb the flow of a light ball, then we reroute the flow of the light ball to this heavy ball. Or now this heavy ball is responsible for all the points which was being served by this light ball. And we repeat this process until the heavy ball doesn't have enough available capacity, and then only we go ahead and select a light ball in my solution. So this ensures that we do not waste much available capacities. But note that here, even if a point is not inside the red heavy ball, I might end up assigning it to the red heavy ball, and that's why we need the expansion of the balls. However, I need to make sure that we expand the balls by at most a constant factor. So at the termination, for each light ball, either it is selected in the solution, or otherwise its flow is absorbed by a heavy ball, or that means it joins the cluster of the heavy ball. So now let me talk about the expansion factor. So let us consider a cluster of a heavy ball. So we have this central heavy ball, and around this heavy ball, we have the light balls whose flow were absorbed by the heavy ball. Now, there can be two cases. If the heavy ball is the largest ball in this cluster, then I can expand this heavy ball by a factor of 3, and all the points are at most 3 hops away from the center. And thus I can cover all the points inside the cluster by 3-factor expansion. However, the pre-processing step incurs a 3-factor expansion for the heavy balls, and that's why in this case I need in total 9 expansion factor. In the other case, the largest ball is a light ball, and in that case I can expand this light ball by at most a factor of 5 and can cover all the points inside the cluster. So all points are at most 5 hops away from the center of this largest light ball. And pre-processing doesn't incur any expansion for light balls. So in this case, the expansion factor is exactly 5. So in total, we obtain a 9-factor expansion. But remember that I said that our expansion factor is only 5. And to ensure that, what we do is we basically remove the pre-processing step. And note that the pre-processing ensured that each point gets at least a constant amount of flow from heavy balls. And if we don't have this condition, then the analysis of constant approximation doesn't work. However, what we do is we use the third idea. So we divide the points into 2 disjoint point sets. P1, the points that get at least a constant amount of flow from heavy balls. So for these points, the condition is already satisfied. And the points P2 for which the condition is not satisfied. And then what we do is we construct 2 auxiliary LPs, P1 and P2, and we compute 2 LP solutions. And we round them independently. Now note that the LP solution corresponding to P1 satisfy the condition, and that's why we can use the algorithm I mentioned before. However, for the solution corresponding to P2, we need a separate algorithm. However, here we have a major issue that even though the points are not shared, the balls are shared, and hence I might end up opening a ball in both of the solutions. So so a ball might be opened in 2 solutions, but this is not permissible. I am not allowed to make 2 copies of the ball. But what we could show is we could show that one can find LP solutions for the 2 auxiliary LPs where only light balls are shared. And then what we do is we scale the capacities of the light balls. So for the auxiliary LPs, I set the capacity of each light ball to be 1/10 of the original capacity. And when we round the 2 solutions, in the first solution, we ensured that we use only UI prime capacity, so we do not violate the capacity. And in the second LP solution, we violate the capacity by at most a 9-factor. So in total, I use at most 10 times UI prime capacity, which is at most UI, and hence we do not violate the capacity. So we obtain a constant approximation with only 5 expansion factor. So for details, I would recommend reading the paper. So we showed that we can obtain constant approximation with 5-factor expansion in the monotonic capacities case and 4.2-factor expansion for uniform capacities. And many questions remain open. One interesting question is to reduce the gap between 3 and 5 for MMCC and 3 and 4.24 for MCC. And also another interesting problem is to study the non-uniform case of the problem. And also, is it possible to obtain a constant approximation in the Euclidean case without any expansion? And with that, I conclude this talk, and thanks for your attention.